Hello and welcome back to Life in the Universe. We are going to move into a new realm of discussion, and that is going to be on the nature and evolution of habitability. And what's going to be, I think, fun for you for this particular module is that we're going to actually talk about the evolution of our star, and we're going to talk about the evolution of the Earth based upon its response to the evolution of the Sun. And it's going to place our solar system and our own Sun in, it's going to set us up, I should say, for putting our solar system and our Sun in the broader context of other solar systems. We will end up eventually talking about the fact that there are many different types of stars in the universe, of which our Sun is just actually a very garden variety version of stars. And one thing that's nice about our garden variety star is that it is stable for billions of years, on the order of 10 billion years. And we'll find out that some stars are not stable over such lifetimes. In fact, some stars are stable only for, say, about 100 million years, which is a flash in the pan, as you can tell from our discussion of geological time. And some stars, though, actually can live up to 50 billion years, which is 5 times longer than the age of the universe. So what kind of star would you like to grow up around? We happen to grow up around one that's in the middle that has about a 10 billion year life. And so during this particular lecture, we'll spend some time talking about the evolution of the Sun and how it has changed with time and how much more time it has left to live and support the planet. So one of the first things we're going to do with our learning goals is talk about something called the habitable zone. And this is a region around a star. It's kind of a spherical shell, if you will, around in space around the star, at which the energy from the sunlight is just the right intensity. It's not too intense, and it's not of too low of intensity. So we're going to talk about this habitable zone in particular, and we're also going to maybe briefly talk about if life could exist outside the habitable zone. But once I define the habitable zone, you'll know the answer to that already is yes, because we've talked about Europa and a little bit about Mars, which we'll see is outside the habitable zone, and even the possibility of something like life on Enceladus, for example. But certainly something like Europa could be a habitable planet. So you can have habitability outside the habitable zone. We already discussed a little bit about why Venus is so hot with this runaway greenhouse effect, but we will go through that argument again. And we'll talk about the importance of a planet's distance as well as a planet's mass in determining how far it should be from a star to remain habitable. So it depends on both properties. When we talk about habitability, we're going to be talking about surface habitability, which effectively is limiting all of our discussion to planets in which liquid water can be pooled on its surface. So the liquid water present and stable on the surface of the planet. Okay, and we'll talk about the boundaries of our habitable zone. Where's the inner boundary of that shell? And where's the outer boundary of that shell in our solar system. And we're also going to talk about how that shell is evolving. So it doesn't stay at the same thickness and the same distance from the sun. So you can sort of think of this shell around the sun where if you are inside that shell, the intensity's too high for liquid water to be on the surface of the planet, kind of your Venus situation, or if you're outside that shell, then your light energy is too low and you might go into a permafrost situation, somewhat like we've seen Mars do. And then you have this Goldilocks zone, and it has a thickness to it. And so what I'm saying is that the thickness of that shell and also the distance of the average distance of that shell from the sun change with time because the sun is changing with time. And you probably could put two to two together, realize it's the luminosity of the sun, or the amount of brightness and the light energy that comes off the sun, that is changing with time. And we're going to talk a great deal about how the sun used to be dimmer in the past and will become more luminous in the future, and therefore causing the shell to move outward with time. Okay. And then we'll talk a little bit about something called the young faint sun paradox, and we'll talk about the resulting evolution of the planet Earth, and when will it shut down the ability to be habitable, when will life begin to die on the planet due to the sun's evolution. Now I'm showing you a slide which is, in a sense, showing you this region called the habitable zone around the sun, and we'll define the habitable zone here. So in the image to the right, you see the sun in the center, you see the Earth's orbit shown as this pretty much circular orbit, and then you see this light green donut around it, and you see that the Earth is actually, its orbit is inside the inner region of this donut. So this donut is called the habitable zone, and you can see that if the Earth's orbit is 1 astronomical unit away from the sun, you can see that it goes out from about maybe 0.85 or 0.95 of the Earth's orbit, or astronomical units, to about 1.2 or 1.3 times the astronomical unit, or the Earth's orbit. Just for reference, the Earth's orbit is on average 93 million miles, or about 150 million kilometers from the sun. Okay. Now, this green area is defined with a few assumptions. Basically, one of the assumptions is that you're going to have an Earth-like planet, sort of a terrestrial, rocky planet, Venus, Mars, Earth-type planet, and that it's going to have an atmospheric composition on it that is, pretty similar to what the Earth's present-day composition is. Now, if you change the chemistry or the composition of the elements that and molecules that are in the atmosphere, say it was more like the early Earth's atmosphere, then the response of the planet to how far away it is from the sun changes. And so basically what I want you to understand is that this is defined by saying, if you have an Earth-like planet, then what are the distances from the sun? What is the range of distances from the sun at which liquid water could exist on a stable on the surface of that planet? And so that is the clear definition is the region or distance range from the sun or central star in which liquid water could be stable on the surface, I'm emphasizing on the surface of the planet. And again, this is an Earth-like planet. So you can imagine for a fixed kind of planet atmosphere and planet mass and whatnot, like an Earth, that as the sun was more luminous, that its energy would be more intense, and so it would make the habitable zone be out further. And if the sun was less luminous and less energy was coming off it per second in the form of light, then the habitable zone would be a smaller donut. Now again, this is a flat picture, so it's a donut. But in actuality, I want you to realize that the Earth's orbit is in a plane, just like on the paper. It does orbit in a plane, but it's a sphere, actually. You could just imagine that of turning this donut into a three-dimensional sphere around the sun. Okay, so again, I want to remind you that this is it implies Earth-like planets. Okay. Now in the yellow box here, I just want to remind you again, and I said it in the previous slide, that We do see under subsurface liquid water oceans, say in Europa, due to tidal heating around Jupiter. And so I just want to remind you that this definition of the habitable zone is surface water only, but but habitable zones are not the only distances or regions around stars where you can have habitability in terms of those three requirements: the chemicals, the energy, and the liquid water. Okay, this particular slide is a repeat of many of the points that I've said in the previous slides. It's just nice to have it written down in bullet form for you. So I say there's some additional thoughts, but in fact, I've kind of verbally stated all the additional thoughts in the other slides. But first of all, it's a range of distances on which worlds that are similar to Earth would exist, such that they would have liquid water stable on their surface. That's bullet one. The number two is I want to remind you that it's not the sufficient reason that would make a world habitable. Your moon or your planet does not have to be in the habitable zone around the star in order to be habitable. Okay, but the habitable zone is a region. It is a place in space. It's not on a surface. It's not around a moon. It's not around a giant planet like Jupiter. It is a spatial volume located around a central star, based upon the idea of if you had Earth-like planet, what range of orbits could it be in? Okay. And then the last one is that I want to remind you that the habitable zone does evolve with time, because stars like the sun brighten as they age. So we expect the habitable zone, therefore, to move out with time. And in fact, at one point in time, Earth was actually on the outer edge of the habitable zone. And as the sun aged, Earth has been entered into the habitable zone. As you can see now, it is very close to the inner region of the habitable zone. And if the sun, as it evolves and gets brighter, the habitable zone will move out beyond the Earth's orbit, and Earth will not be in the habitable zone anymore. And so what does that mean? So you'll have to stay tuned to the rest of the lecture for that. Now, in summary, any time in the star's life, the habitable zone is this range of distances. It's a spatial location around which the planet could potentially have these conditions of liquid water on its surface. Just trying to really drive this point home. Now, in the diagram to the right, we can see now the habitable zone in context of the other planets in the solar system. We see Mars in its highly elliptical orbit in the inner region there, and we see Venus's orbit, which is well inside the habitable zone. And we all know that Venus doesn't have liquid water on its surface today. And then we have Earth, which is in the inner region of the habitable zone. And it's nice because they've shown a little bit of the elliptical nature of Earth's orbit here. You can see that to the left, it's very close to the inner region, and to the right, it's a little bit deeper into the habitable zone, suggesting that this 3% out of round of Earth's orbit is actually real. It's not just a circular orbit. And then we have Mars's orbit, which is about 9% out of round, and we can see that Mars, at one point in the upper right, around the 1 o'clock position, comes pretty close to the habitable zone, to the outer region of it, but spends the rest of its orbit very clearly outside. And you can see around the 8 o'clock position, when it's at its aphelion, it's quite far from the edge of the habitable zone. Now, if you remember when we did our module on Mars, I told you about the elliptical Martian orbit, and that it was about 50 million miles difference between its closest approach to the sun and its farthest approach or extent from the sun. So that's a quite large range, and that range is about 1/3 of the distance from the Earth to the moon. From the Earth to the sun, up to about 1/3 of that distance. So that's something to think about. Anyway, in the upper box we see Venus inside the sun's habitable zone, Mars outside the habitable zone, and Earth close to the inner edge of the habitable zone. Okay, so we studied the greenhouse effect, and just to give you the brief reminder on that, I'll give you the reminder of the greenhouse effect because it turns out it's going to be very important for how it enters into the calculation of that habitable zone around a star. Now, the greenhouse effect, if you remember right, was the fact that visible light from the sun is the Earth's atmosphere is very transparent to visible light from the sun. So the sunlight comes down from space, hits the Earth's surface, and it heats the Earth's surface. Now, hot objects will radiate light, but they radiate most of it in the infrared. So it's infrared light is being emitted back from the surface of the Earth. Now, infrared light does not pass easily through the atmosphere. It gets absorbed, and it tends to get absorbed by that now known as somewhat evil molecule, carbon dioxide. But it's not evil, just putting too much in the atmosphere could have bad effects. Now, so the infrared light that is emitted from the surface of the Earth, heated by the visible light from the sun, gets trapped in the Earth's atmosphere and will warm gets absorbed, and its energy gets absorbed into the carbon dioxide and methane and water vapor molecules, and they therefore heat up the rest of the atmosphere, and that of course heats the Earth to make it more room temperature. So that is the basic idea, again, remind you of the greenhouse effect. And what I want to do here is show this table 9.1, which would give you some indication of how effective or how much the greenhouse effect has an impact on Mars, Earth, and Venus. So let's start with Venus, which we know is inside the habitable zone. We discussed briefly its runaway greenhouse effect. We will again discuss that a little bit later. But Venus has an average surface temperature around 470 degrees Celsius, which is, give or take about 900 degrees Fahrenheit. So twice the heat of your oven on broil. So I wouldn't want to put your hand too close to that. Oh, but wait, the pressure of the atmosphere is so thick, it's like you're 2 miles below the ocean, so it basically crushes your head in your hand. So I wouldn't, worry too much about that environment. It's pretty, toxic for humanity. Now, interestingly, if there was no greenhouse effect on the planet, it would be a chilly minus 43 degrees Celsius on average. Now that is 40 degrees below freezing of water. So basically, if there was water on Venus, it would all be frozen, and it would not really be a habitable environment by the likes of our 3 criteria. That is a whopping 513 degree change in temperature due to the greenhouse effect. From minus 43, of which it would be, then the greenhouse effect rises it to 470. So the difference, the third column on your right, is 513 degrees, that it's raised the average temperature of the atmosphere. That's a tremendous effect, and the reason it's so tremendous, as we know, is that there's just tremendously high concentrations of carbon dioxide, so it's a very efficient process on Venus. Now with Earth, the average temperature is around 15 degrees Celsius, which, is 70 odd degrees, 60 odd degrees. Well, I'm sorry, on average. We're talking about the average. So the average is around 55 to 65 degrees or something like that. It's actually pretty chilly when you average it over the whole globe. Now, without the greenhouse effect on Earth as it acts today, it would be minus 17 degrees Celsius. So again, we see that the Earth would be frozen over in a big snowball if we didn't have the greenhouse effect. So greenhouse effect is your friend. You just don't want too much of it, and then it's not your friend, it's your enemy, like it would be on Venus. So the temperature difference is 32 degrees on Earth. In other words, the greenhouse effect raises the temperature of the Earth on average about 32 degrees. On Mars, Mars is minus 50 degrees Celsius. It's very, very cold. But interestingly, if there was no greenhouse effect, it would be minus 55. So it almost seems, and I say almost, as if there really is very little greenhouse effect operating on Mars. And it really is just a very little effect. So it's about a 5-degree effect, a 5-degree warming. And so I do want you to understand the greenhouse effect does operate on Mars, okay? So even though it's cold, even though its atmosphere is only 0.7% of the pressure and thickness of Earth's, it is mostly carbon dioxide, and that very thin carbon dioxide atmosphere helps raise Mars's temperature about 5 degrees Celsius. Now, something very interesting to think about. Without the greenhouse effect, all of these planets would not be habitable, okay, would not have liquid water on their surface, okay? That's what I mean by habitable in this case. I should not throw that word around too loosely, because habitability was based upon our 3 criteria: elements, energy, and water. But basically we're talking about they would not have liquid water. So all these 3 planets would not have liquid water on their surface. This is very important because it is illustrating very clearly that your calculation of the habitable zone around the star depends upon planets having greenhouses effect. That calculation of that green donut, as you will, that we showed in the previous 2 slides, those distances from the sun are predicated on the fact that you have an atmosphere on the planet and that the greenhouse is operating on it. Okay, and so that makes this mathematical ring, or this mathematical donut or shell around the planet. Okay, but interestingly, thank gosh we have the greenhouse effect, because otherwise even the Earth would not have liquid surface water. Okay, so we've discussed the habitable zone in terms of now of the greenhouse effect's role, and so we see that the chemical makeup of the different molecules that are in the atmosphere and the thickness of the atmosphere play a role in the calculation of the habitable zone. And now we want to talk about the role of the planet's mass, and also the role of the planet's distance. So this slide is a role of distance. And I think the distance argument's pretty obvious already, not to mention that I think I've mentioned it twice already. You know, as the planet's further from the sun, you know, you have this inverse square law of light. And so planets that are twice as far away receive 1/4 as much light, or planets that are half as far away receive 4 times as much light. So you see, you have this situation where it's very sensitive to distance. Okay, now let's look at the relative distances of Venus, Earth, and Mars, since we've been comparing them. Earth, we've talked about, is about 150 million kilometers away from the sun, and if you compare Venus, it's only about 100 million kilometers from the sun, only 100 million, and Mars is about 230 million. Now, it turns out that it's easier to talk about those distances in terms of astronomical units. So if you go 1, 2, 3, if you go to the 4th column, it says distance from the sun in AU, or astronomical units. The Earth is one of those units, and so 1 astronomical unit is 149.6 million kilometers. And the distance of Venus is 72% of that distance, which turns out to be 108 million kilometers, and Mars is 1.5 times that distance, which turns out to be about 230 million. Now remember, those are average distances. Now, if you go to the radius at the equator of the planet, you can see that Earth is around 6,400 kilometers and Venus is around 6,000 kilometers. And so you can see those two planets are roughly about the same radius, about the same size. Okay. Mars, we found out, is actually quite small, and so it has a radius that is about half that of Earth and Venus. Now it's interesting that Earth and Venus, in this sense, are kind of sister planets. They're just about the same mass. They just happen to have very different orbits. Now, in terms of normalizing the radii to the Earth's, we have the last column on the right, the radius in terms of the Earth. So we define the Earth as 1 Earth radii. And so you can see that Venus is 95% of the Earth's radius. It's just a 5% smaller. And like we said, Mars is roughly around half, 0.5 times that of the Earth. So Mars is 50% of the size of the Earth and 50% farther from the sun than the Earth's. Okay, so in Mars's case, both mass and distance differ greatly for this planet compared to the Earth. In the case of Venus, it has roughly the same size and roughly the same mass as Earth, but its distance is only about 70% from the sun of the Earth's distance. And so you can see that Earth and Venus have some things in common, but Mars definitely is its own beastie, its own planet in that sense. So we'll be talking further about that in the next couple slides. Okay, so we're going to start with Venus, and you'll remember that Venus has about the same radius and the same mass as Earth, but it had a very different evolution than the Earth, and so the one variable that's different, of course, is its distance. So one of the things that we want to talk about is was there evidence that Venus was Earth-like in the early days? And so there's two things I want to describe really quickly, and one is that the carbon dioxide that is in the atmosphere of Venus is equivalent to what you would expect if Venus had been Earth-like. And what do I mean by that? Well, it turns out that Earth has a lot of carbon dioxide. A lot of it's in the atmosphere, but most of it is in the mantle. It's in the liquid mantle. It's outgassed by volcanoes. Through that, it is dissolved in the oceans, so that, if you take a big scoop of water, there's a lot of carbon dioxide gas also in there, and it's locked into rocks, carbonate rocks, silicate rocks, and some of this is through the process of living matter as well that locks that up. Now, if you took all those different various forms of carbon dioxide on the Earth and you took it out of the mantle, took it out of the water, took it out of the rocks, and put it in the atmosphere, guess what? You get sort of about the same amount of carbon dioxide in the Earth's atmosphere that Venus has in its atmosphere. And so this makes us think, well, if Earth had gone through the process that Venus did and become an arid runaway greenhouse effect, that it would have an atmosphere with about as much carbon dioxide as Venus does. So that's one reason we believe Venus may have been Earth-like, because it certainly has the carbon dioxide budget that Earth has. The second one was, could there have been oceans in the past? And so what I'm going to do on the next slide is argue for you an inductive reasoning for inferring that there were oceans in the past on Venus, and it's a really quite a good argument. But again, it's an argument of inferring that there were oceans from an inductive logic. And so it's not something we can prove, but it's something that we can definitely induce. So, water on Venus? If so, what happened to it? Well, let's see if we can first, with this slide, talk about the evidence for water on Venus. And then in the next slide, we'll review our storyboard of what possibly happened and why Venus lost its oceans if it had it. So we know today it's too hot for water to be chemically locked into any surface rock or any of that. So this is about the most absolute arid planet you could absolutely imagine. The lithosphere and the mantle both are extremely quote-unquote dry of water. So of course, people have to start with two guesses or a hypothesis, and you can sort of say on the one hand, Venus never had water to form the oceans, and then try to figure out what kind of evidence would demonstrate that that was true. Or you could say possibility two, Venus once had large oceans. You sort of bracket the possibilities. There could have once been ocean content that was similar to Earth's, but it's all been lost. Okay, so we think that two is more likely, and now I'm going to give you the evidence for that. And it's really a very interesting set of inductive reasoning process. So first of all, let's talk about the fact that water molecules are made out of oxygen and two hydrogens. Okay, well, hydrogen is the most fundamental atom. It only has one proton in its nucleus and one electron orbiting it. But the universe does make an isotope of hydrogen, and that isotope of hydrogen is called deuterium. Deuterium in its nucleus has one proton and one neutron. So basically, you just stick a neutron onto the proton, and you have a deuterium nucleus. It's still hydrogen by definition because it has one proton that defines it as hydrogen. But it also has this neutron stuck to it, so it's twice as heavy as a regular hydrogen. Now, it still only has one electron orbiting it because it has to balance out the charge with the one proton. So, deuterium. Deuterium is hydrogen, but it has a neutron stuck with the proton in the nucleus and is twice as heavy. Sometimes people call it heavy hydrogen. Now, the universe made hydrogen and helium during the Big Bang, and when it did so, for every deuterium atom that the Big Bang made, it made about 100,000 or maybe 200,000 regular hydrogen atoms. Okay, so that's important. So basically what we're saying is that out there in the universe, if you scoop some matter up and you count the hydrogens, for every 200,000 hydrogen atoms that you pick out of this scoop of material, whether it's gas or our Earth's oceans for matter, you're going to find one deuterium for every 200,000 hydrogens. Okay, so that is a cosmic abundance. And indeed, if you go and you take a glass of water out of our Earth's oceans and you separate all the hydrogens from the oxygens, and then you count all the hydrogen atoms, for every 200,000 hydrogen atoms, you're going to find one deuterium isotope. Okay, so that's the important piece of information. Now, this is very powerful because everywhere we look in the universe, deuterium has this relative abundance. Now, if you go someplace and you find that the number of deuterium isotopes is different than the cosmic abundance, then you know something happened there. And that's what we find on Venus. Okay, what we find is that the deuterium abundance on Venus is 135 times higher than it is on Earth, than it is if you pulled up any random scoop of material, say a scoop of matter out of the sun or out of our oceans or out of some gas cloud. for some reason, there's this very high abundance of deuterium relative to normal hydrogen on Venus. Now, how could that happen? And the argument goes like this. So, for any water molecule that might be in the atmosphere of Venus, 2 hydrogen, 1 oxygen, okay? As Venus, let's say, was getting hot and evaporating, the molecules would be disassociated, and basically meaning that the hydrogens were broken off of the oxygens. Now, oxygen is about 16 times heavier than a hydrogen atom, and so it tends to not have buoyancy in the atmosphere. It tends to settle down into the atmosphere. Hydrogen is extremely light, and so it tends to be buoyant and will rise up in the atmosphere and eventually escape to space and be lost to the planet. Now let's talk about deuterium. If your water molecule, say, had a hydrogen atom and a deuterium atom hooked to the oxygen, okay, so it was heavy water in a sense, and those hydrogens, the deuterium and the hydrogen, got knocked off the oxygen. The hydrogen is half the weight of the deuterium. The deuterium is twice as heavy because it has the proton and the neutron in its nucleus. And so the hydrogen would be more buoyant and would escape to space more readily than the deuterium. And so more deuterium would be left behind in the atmosphere of Venus than than hydrogen. And so with time, as more and more of these water molecules were dissociated, more and more deuteriums get left behind on Venus than do hydrogens. Or I should say, more hydrogens escape to space than do the deuteriums, leaving the deuteriums behind, and therefore its abundance is 135 times greater. I should say the ratio of deuterium to hydrogen is 135 times greater. That is a very good set of daisy chain logic for inductive reasoning for the fact that there had to be something that happened on Venus, like this process I just described, that swept away, if you will, evaporated away the regular hydrogens and left behind the deuteriums. All right. Now, when you add up the deuteriums that are available and you do some calculations about how much hydrogen and deuterium had to be on the planet in the past, lo and behold, you come up with a tremendous amount of water. And so even a lower limit on the global ocean, if it was completely covering the planet everywhere, it would be several meters thick. And I think it's very similar to that with the Earth, that I don't know what the average depth of the ocean would be if it was distributed globally around the planet. It's a very interesting question, and one could do some math and figure it out, but I won't do that real quick. But nonetheless, the idea is that Venus has this strong argument for having had a large amount of water, and therefore enough water for a global ocean similar to Earth's, and it's based upon this high deuterium abundance. So that's a very good piece of logic that we use, and I wanted to make sure I tried to explain it as well as I could. So if Venus had all of this water, what happened to it? Okay, runaway greenhouse effect would be the answer. And we've seen this slide before, and I think it was couched in terms of what would happen to Earth if it got moved into Venus's orbit. And in a sense, you could think of Venus as being very much Earth-like, but now the difference being that it's in this smaller orbit. It's closer to the sun. And so basically, the left-hand diagram is showing visible sunlight coming down to the Earth and passing through its atmosphere. And in this middle pictures with the circular arrows is two parts of a process that are very simply put. As you can see in the upper panel, the yellow wavy line coming down would be visible light from the sun penetrating through the transparent atmosphere, hitting the Earth, heating up the Earth. The Earth then radiating this red wiggly line, which is representing red infrared light, and that infrared light then being absorbed by, say, a molecule of carbon dioxide or water vapor or methane, some greenhouse gas that's in the atmosphere. And so therefore heating up the atmosphere and therefore showing you that it's heating up the Earth. Now, if the Earth heats up, we move along our little gray arrow to the bottom panel here, and in fact, that causes more water vapor to arise from the ocean. With water vapor is a greenhouse gas which traps infrared light. So we go back to the top and we see that the greenhouse effect is now more efficient than it used to be, so that more infrared light is being trapped more efficiently and less of it escaping. And so that heats the Earth more. We go around our loop one more time. We evaporate more water, which puts more greenhouse gases in the atmosphere, which means we trap even more infrared light, which means we heat the Earth even more, which means going around the loop to the bottom thing, we got more water vapor, and on and on and on and on and on you go until you run out of ocean and you end up with something horrible like Venus, hot, arid, and a very, very thick atmosphere. So that's the idea of the runaway greenhouse effect. And in terms of global warming, that's one of the things that we would like to avoid. We have lots of sophisticated computer models. Heck, they even help us calculate the habitable zones around stars. But the fact of the matter is, they're just models, okay? And we don't know what the tipping point is to get the runaway effect of the greenhouse. So we just want to make sure we don't get there. And we're going to find out that the sun's heating and it's going to cause a runaway greenhouse effect anyway. So we don't have to move the Earth into Venus's closer orbit. The sun is going to heat up and turn Earth into Venus anyway. It's just going to be on a longer time scale than what maybe the human effect might do. Okay, so here we have the three bulleted slide, which summarizes basically the three things that we've been talking about since the beginning of this particular module. The three factors which allow us to calculate this habitable zone range around a star involve both distance from the star, and they have something to do with planetary mass and atmospheric conditions. So in a sense, distance is really quite obvious. It's because of the inverse square law of light. You know that the further you get, the dimmer the light is, the less energy it contains, the less it can heat the planet, etc., etc. The number 2 and number 3, they're kind of mixed together a little bit, because planetary size, as you remember, is related to how much heat the planet has as a reservoir inside of it, and then also how rapid it would radiate that energy out to space. So it turns out that you have a large planet, you can keep it geologically active for a long time, and you keep it geologically active, you're going to maintain an atmosphere because you're always outgassing. So any atmosphere you lose, you're replenishing with time, and you can develop a somewhat stable situation. Okay, so plate tectonics turns out to be very important because it drives volcanism, which drives outgassing. Okay, we found in the case of Mars that it's much smaller than the Earth. It cooled and it lost its atmosphere and therefore lost its water. Interestingly, we have Venus, but Venus has no plate tectonics and its crust is very dry. Okay, but it also had a lot of water loss result that was more related to its distance from the sun than its size or its mass. Okay. And this is why I say that this is tied together with number 3, the atmospheric conditions, because if you don't have a planet that's able to maintain a stable atmosphere, then eventually it's going to lose the ability to keep its atmosphere, and it's going to lose the ability to hold on to its liquid water. Or in the case of Venus, the atmosphere is going to go through the tipping of the scale to evaporating the oceans and overheating because of the greenhouse effect. Okay, so Mars, it is not replenishing its atmosphere. Okay, and it basically lost most of it. On the case of Venus, it was able to hold on to that atmosphere, but it turned it into a big, thick carbon dioxide, semi ocean, if you will. It's very, very dense and thick. I mean, you can see through it. It's transparent. You can see to the horizon, but it's very blurry, as if you were looking through water at some point. So these are the three things: distance, the mass and geological activity of the sun, of the planet, and then the atmospheric and climate evolution of the planet. All of those go into calculating what are the distances that are the habitable zone. So in other words, calculating the thickness and distance of the habitable zone from a central star are based upon these three things, and they're quite complicated mixture of these elements in the computer model to balance out the energy from the sun coming into a planet. So now that we've talked about the three effects that go into the computer modeling to estimate the habitable zone around the sun or around any star, we see that the planetary mass, distance, and the composition of the atmosphere and the climate evolution all play a role. And so there's some uncertainty in those, and therefore there would be uncertainty in our calculation of what we call the habitable zone. And so for sake of argument, we're going to take a very complex discussion and distill it down to two sort of extreme cases, what we call bracketing the problem. And in one of the extreme cases is what we call the simple greenhouse effect, which is the standard story that we have been discussing, say, with our pushing Venus into, pushing Earth into Venus's orbit type of scenario. Another one called the moist greenhouse effect. And the moist greenhouse effect is one where you allow some of the water vapor to escape into space and from the evaporating oceans as they evaporate. And then also this models the effect that will happen where the carbon dioxide in the atmosphere will actually be more efficiently processed into these exposed carbonate rocks now, and therefore the carbon dioxide concentration will decrease. We'll talk about that a little bit more. Mostly that's going to be in one of the videos that you watch. So what I'll have to say is you definitely want to watch that video. It talks about the fact that this carbon dioxide will be leached out of the atmosphere during this process and will shut down photosynthesis, which is bad for life on Earth. So that happens in about 600 million years, but I'm getting ahead of the story. So you have the simple greenhouse effect and you have the moist greenhouse effect. And effectively, the moist greenhouse effect gives you a more conservative estimate, in other words, a narrower habitable zone than does the simple greenhouse effect, which gives you a more, what we might call a more optimistic version of the habitable zone, which is to say it's thicker. And so you can see in the diagram on the right hand, the darker green is your conservative estimate that includes the moist greenhouse effect. And this has to do with the fact that the planet is not as efficient as warming itself, and so therefore it has a narrower range over which it can exist in liquid water can exist on its surface. So for the conservative estimate, we have this darker green band, and for the more optimistic simple greenhouse effect, we have the broader green band, the lighter green band, and that's obviously a broader or wider habitable zone. So you can see in the conservative estimate, which is the ones that you've seen in our previous plots that include more complicated physics, including this moist greenhouse effect, it goes from about 0.95 astronomical units out to about 1.4. And we remind you that Venus is at about 0.72, so that puts it firmly inside of this range. And Mars is at 1.52, and I think I got those second decimal places right, about 1.5 times further. And so it's definitely outside the 1.4 AU outer lip or range of the zone. So on the optimistic case, we see it would range from about 84% to 1.7 times the Earth's orbital radius, which puts Earth more firmly inside the habitable zone, which would be good for us. And it even puts Mars inside the habitable zone. So that's effectively saying if Earth was in Mars's orbit, we have to ask the question, would Earth have liquid water on its surface? And according to the optimistic estimate of the habitable zone, the answer would be yes. But if we model the Earth's atmosphere according to the moist greenhouse effect, the conservative estimate, Earth would definitely be outside the habitable zone if it was at Mars's orbit, and therefore would go through probably an ice catastrophe process. Okay. So at some critical distance, a planet with suitable mass will still not be warmed by the greenhouse effect due to the point where surface water could be in equilibrium on its surface. Okay, and the carbon dioxide condensing out of the atmosphere, i.e. moist greenhouse effect, really does narrow down this range for the habitable zone. Now, sometimes we have this fact that the habitable zone is called the Goldilocks zone. So it's just right. You know, you've heard of the three bears and whatnot. Mama bear, Papa bear, and baby bear. And Mama bear's porridge is too cold and Papa bear's porridge is too hot. So in a thing, you could think of Mars as being Mama's porridge and Earth being baby's porridge and Daddy's Venus orbit being Papa's porridge. So that's my magic word for the day is Papa Bear. Okay, well, welcome to the astronomy portion of the course. We are definitely going to be doing some astronomy 101 here. We're going to end up talking about the sun as a star, and we're going to talk about the sun's evolution with time and how long it lives, how its luminosity or energy output changes with time, how its size changes with time. Its mass effectively will stay constant with time. So basically in the top panel to your right is a diagram which is to scale in terms of the distances of the objects, where that distance from the sun center to the Earth center would be 1 on that scale, 1 astronomical unit. And you can see that Mercury is 0.4 of that, and Venus is 0.7, and Mars is 1.5. Great, but please do remind yourself that the sizes of those objects are completely wrong. You couldn't see them on this scale. The sun itself, though, is quite huge compared to the size of the Earth, and it's not to scale there by any means. Now, these are sort of bad pictures, but if you go down to the second panel, you can see what the sun's going to be in about 7.5 to 7.6 billion years from now. Okay, now it's interesting that what we're trying to show in this diagram is that the sun is growing in size. And these are really poor diagrams for knowing the relative scales. But basically what I want to let you know is that the sun will be so big that it will engulf Venus's orbit in around 7.58 billion years from now. And it's growing rapidly at this time, so that by 7.59 billion years from now, the Earth's orbit will be engulfed. So what I'm telling you is that the Earth and Sun system are going to evolve. The Sun is right now, I guess what I should say is, in the future, around 7.5 billion years from now, the Sun will be over 100 times its present day size, and that will put it out to the Earth's orbit. So in that sense, you have to think about the Sun is going to really bloat out. And this process is quite complicated. So I don't know whether I should talk about it in so much detail, but effectively, in the next diagram, I'll describe this in more detail, but I'm going to go through it in a little bit now as I go through the text on the left-hand diagram, part of the slide. So the Sun will expand, and the question will be, well, why is the Sun expanding? And so, try to picture this and listen to this part. It's really some really good astrophysics that very few people in the world know about. And why is the Sun going to expand and die? Okay, so let's think about what the Sun's doing. And this again is described pretty well if briefly in the video that I want you to watch. I think it's video 1 that goes with the module. So the Sun is basically a big ball of gas. It's crushing down on itself under its own weight, and the center part is experiencing all of that pressure from all of the layers above it. And so the core itself is very dense, and it's very, very hot. And it's so hot and dense that all the electrons are stripped off of the nuclei, and you have this plasma down there. Fast-moving particles that are very, very compactly tight together. It's 150 times denser than water down there, so it gives you a feeling how dense it is. These particles are zipping around very rapidly, and so when two protons, the stripped hydrogens, collide with each other, it turns out that they'll stick together in a process called fusion. You can sort of think of it as when they touch, there's sort of like a strong nuclear force, and I don't know, just for fun, picture it as crazy glue. When they touch, they stick. And they release energy in this process through Einstein's E equals mc squared equation. I'm not going to go into all the physics, but every time two of these protons stick together, they release energy in the form of gamma rays or light energy. And that gamma ray then works its way out of the Sun, losing energy as it goes out, and finally, 1 million years later, reaches the surface and goes out into space. And those are finally the light particles that were created 1 million years ago are reaching us today from the surface of the Sun. Now, with time, as these protons stick together, they actually have turned themselves from hydrogen into helium. And so what's happening is you're building up helium in the core of the Sun while you're trying to fuse hydrogen. Okay, so you can think of helium as sort of a soot or an exhaust product of this. And it gets in the way. These particles, these helium nuclei now get in the way of the other protons colliding and sticking together. And so the Sun has to work harder. It's kind of like building up sludge in your car engine. You have to push the gas pedal harder to get the same kind of performance out of it that you used to. So the Sun has to basically pick up the rate at which it's doing fusion. And it's doing a lot of the fusion. It's presently doing 10 to the 38 fusion reactions per second. Okay, it's a huge amount of, I can't even fathom how fast that is. Okay, so it has to do it even faster because of the helium building up and getting in the way. And as it does that, it turns out the only way it can do that is if you allow if you somehow make the hydrogens move around faster. In other words, like stepping on your gas pedal more. And that means you have to turn up the heat in the core. So basically the way that happens is that the core contracts a little bit, and that allows it to accept even more pressure and therefore get even hotter, and then it cranks up the fusion in the core, and and the hydrogen can get around the heliums now better, and you can continue to keep your star in balance from its own gravitational self-contraction, pulling down on it. Now, when the core heats up, this is the tricky part. When the core heats up, the energy gets dissipated outward, and it causes it pushes harder on the outer envelope or the outer regions of the star. All that extra heat coming out of those faster nuclear reactions, all that greater amount of energy per second pushes the star outward and makes it bloat. So even though the core got smaller and is cranking itself harder, that forces the star to expand because of that extra energy coming out of the core. And so eventually what happens with time, you're building up more helium, you're having to make your core get smaller and get hotter, which is causing your outer part of your star to expand more. And with time, your star bloats out to be 100 times bigger than it is today. And this is called the red giant phase, if you will. Okay, and so it basically continues to build up helium and sludge in its core, and somewhere around 12 billion years from now, it will hit the point of no return, where it cannot actually continue to fuse hydrogen in its core, and so it starts to go through this hiccup phase, turning on, turning off, turning on, turning off, and those hiccup phases actually cause the star to expand and contract, expand and contract, expand and contract, and it pushes the outer layers of the sun off. Every time it expands, it kind of ejects some of the outer layers, and you're going to eventually get this huge nebula of gas, which is going to expand beyond the size of the solar system. And we have a name for this big expanded gas around the solar system. We call it a planetary nebula. And it's a historical name, has nothing to do with planets. Of course, all the planets by now are vaporized and part of that big gas cloud that was the sun. But basically what you have left over is a little star in the center, which was the core of the sun, which we now call a white dwarf, and it turns out to be about the size of the Earth is today. It's very small. And then the rest of the star has gone out into this big gas cloud, and it has vaporized all of the things in the solar system, and you have this thing called a big nebula, called a planetary nebula. That's what's going to happen to our sun. Now, if you were taking Astronomy 110, I would tell you what happens with supermassive stars, but they don't die in this sort of whimper of a death like the sun's going to. They actually go through a process where they basically collapse in on themselves and explode. And explode they do. They really blow their brains out. There's hardly anything left over when they've exploded. And in the 1 second of their explosion, they release more energy than the sun does during its entire 12 billion years of existence. So that should tell you something about how big that explosion is. Okay. So anyway, the sun will not become a supernova. It will not explode. It's going to die with quiet dignity and not in a big suicidal death plunge. Okay. Now, when we talk about what does this mean for the Earth, we get a little bit more nervous. Okay, so how long will the Earth be habitable given this process that the sun's going to go through? And the estimates are, depending upon whether you use the optimistic or the pessimistic habitable zone, it should be around somewhere between 1 and 3.5 billion years before the runaway greenhouse effect on the Earth will take effect. And I'm going to show some more of that in the next slide. You're going to get a little bit more astronomy and some more details with the sun's evolution. So somewhere between 1 and 3.5 billion years, the greenhouse effect will become runaway. Now, in the lecture, in the module lecture, we're going to talk about, when is the Earth going to go runaway greenhouse effect and sort of take the path of Venus. But in the movie, you'll see that photosynthesis shuts down even earlier, say at around 600 million years. So life is going to have a hard time. A lot of life will die in about 600 million years from when the star starts to expand. Okay, so let's move on to the next slide. Okay, here's our second astrophysics slide, if you will. And this is the story of the sun a little bit more graphically. And it's complicated, but it's also, in a sense, a storyboard. So if you can bear with me in the form of a storyboard, I think you can follow along. Now, you'll see that I have a table in the upper left, and I have each of the stages of the sun's life. In a sense, it's a continuous evolution, but we can talk about certain milestones along the way. And there's 7 of them, 1 being born, 2 basically now, 3 is something called the subgiant phase, 4 is called the helium flash, 5 is called the helium burning phase, and 6 is the supergiant phase, and 7 is called the nebula phase. And we talked about the planetary nebula at the end. Then you'll notice that below the table, I have something called the Hertzsprung-Russell Diagram. And when I say welcome to Astronomy 101, this diagram is a bread and butter diagram of all astronomy. You cannot learn astronomy or learn about astronomy and not have seen this Hertzsprung-Russell diagram, also known as the HR diagram. So I'll be calling it the HR diagram from this point forward. Now the HR diagram plots 2 properties of the star against each other and places the star on the diagram based upon its properties. Those 2 properties are its temperature on the surface, so the temperature we measure on the surface of the star, and also the luminosity of the star. Now, the luminosity star is basically the amount of energy in the form of light that's emitted from the star every second. It's the power output of the star, energy per second. It's power. And so that's the power output of the star in the form of light. Okay, and so we measure that. We measure it by collecting the star's light and how fast the light's coming at us. Well, it's always coming at the speed of light, but the intensity of the light coming at us. And we can measure the star's luminosity. And then we could take the spectrum and measure the star's temperature. If you remember, I told you about how spectra you can use to measure temperatures. So you take the spectrum of a star, you measure its brightness, and you get its luminosity, and you get its temperature. Okay, and then you can plot that on this diagram, and each point here is a star with a different temperature and different luminosity. Now, you can see that where we have point number 1, where it says sun, that would be where the sun lies on this diagram. It has a temperature just under 6,000 degrees. You can see the temperature scale along the bottom, and just under 6,000 degrees. And it has a luminosity in terms of sun luminosities. These have all been normalized to luminosity of the sun, just like we did with the Earth's radius, or 1 AU is the Earth's orbit radius. So it has 1 solar luminosity, and so you see where it falls on the diagram. We have lots of other stars. We'll be talking about them in the next module in more detail. We have stars which are cooler and have lower luminosity. So that puts them lower on the diagram for the lower luminosity, puts them more to the right because cool temperatures are to the right. And we see that there are these red points down at the lower right-hand corner. Those are cooler, less luminous stars than the sun. We also know that there are stars out there that are more luminous than the sun and hotter than the sun. And so if you go to the upper right of the diagram, you see the blue larger stars there. They can have up to 100,000 to 1,000,000 times the sun's luminosity. And they can have temperatures that are around 30,000 degrees. And we give each of these stars letter names based upon their temperature only. And it's a long historical story for that, but guess what? We'll talk about that in the next module. But hot stars are basically O stars, and cool stars are M stars. The sun is a G-type star, right there, sort of in the middle, around just under 6,000 degrees. Okay, so basically, stars that are in their midlife, that are stable, and they're not in their dying process of their life, fall along this nice this nice sequence here that we see from the lower right with the red stars up to the up to the upper left with the blue stars. And this is a sequence called the main sequence, and we'll talk about that more in the next module. But for now, I just want you to think about this diagram in terms of the sun. So let's just look at the sun. And we can see that I've numbered each of these stages of the sun's life on the diagram, showing you what its surface temperature and what its luminosity will be like at these different stages as it ages. Okay. Now, let's go to the right-hand side of this diagram. And in the upper, where the blue curve in the diagram there, we are plotting the sun's luminosity, okay? And so the sun's luminosity is plotted as a function of time. And it's a log scale, so you can see that you have 1, and then you have along the y-axis, you have 1, then 10 times, then 100 times, then 1,000 times, and then 10,000 times. So we're talking about a large dynamic range of luminosities, but the log scale lets you squish it down so you can see it on one little plot. Now, 1, of course, is when the sun was born, and that would be at time equals 0. So along the x-axis of our diagram, we see the time given. Now, this is a really funny diagram in terms of the way time is plotted. First of all, from 0 to 12, you see it's plotted in billions of years. So each one of those tick marks is 1 billion years. Okay, so basically you can see that at 0 time, the sun was born. And you can see that its luminosity, it had dipped down to about 70% of what it is today. And you also now can see that today, now step 2 is about 4.6 billion years later on the diagram. So you move along the axis, and you can see that the now is sitting above 4.6, and that the luminosity today is 1. So basically that is today's solar luminosity. And then, of course, what we're going to see as we move along time, that the luminosity is increasing, and the blue curve is getting higher. And then, after 12 billion years, notice that the curve, notice that the x-axis changes from 12.1 billion years to 12.2 to 12.3. And so now we see that every tick is 100 million years. So basically, we've expanded out only a 250 million years into a larger region. And so this is showing you that what happens between steps 3, 4, and 5 are only happening over about a period of 250 million years, or about 300 million years, rather than over billions of years. So it's they've expanded the axis. And then when you get beyond 12.36 billion years or so, it expands even further. So now every tick is, say, about 100,000 years. Okay? And you can see now that we're talking about a period of time that is much shorter, but you can see a lot of activity is happening out at that period of time. Okay, so that's the upper plot showing you how the sun's luminosity changes with time. And you can see that between 3 and 4 that it increases dramatically. Okay, and then if you go down to the bottom axis with the red curve, it's the sun's radius versus sun's age. The time axis is identical with the same expansions at 12 billion years and 12.36 billion years. And this time we talk about the sun when it was born at 0 age, and it was about 80% or 90% of its present radius. And as it's moved from stage 1 to stage 2, it has slowly grown out now that it's 1 times the sun's radius, or which is actually 10 to the 10 kilometers. It's a huge number. But in terms of that unit of 1 solar radius, it today is that number, 1. Okay. Again, it's growing until it gets to be about 12 billion years, and then it takes off. It expands dramatically over the next 300 million years, and we see that the sun's radius gets to be almost 100 times, a little over 100 times its present size. Now, I want you to notice that dashed line across the top there at around 200 times the sun's radius. And it says present radius of the Earth's orbit. And you can see what I'm telling you is that the sun is going on out to the size of Earth's orbit. So that does not bode well, that the sun has become so large that basically the Earth is going to be engulfed in it by stage 4 here. Okay, let's then talk about what's going on here with all of this chart. So let's go to the table. The second column is the age in billions of years, and so that gives you where to look along the x-axis of our diagrams on the right-hand side of the page. And then we have the luminosity, the next column over, in terms of the sun's luminosity. And we can see today it's 1, and in stage 3 it's 10% more, and then it grows up to be 10,000 times more eventually when it gets to stage 6 and 7. And then we have the size of the sun, r over its present size, is the very rightmost column. And we can see that in terms of, okay, so that number actually isn't in terms of the sun's radius, it's in terms of the Earth's orbit. So today, for example, the sun is 0.5% of the size of the Earth's orbit. So it's this little thing that's less than 1% in size of the Earth's orbit. That shows you how far we are from the sun. Okay. When it's at stage 4, it will be the size of the Earth's orbit. So that's what this is telling you here. And it's not shown here, but it actually, they didn't show it on the diagram below, but when it's a supergiant, it actually goes out to twice the Earth's orbit. That's stage 6. And, that would be off the chart here on the other side. So we don't show that. But at stage 6, it goes all the way out past Mars's orbit. So even Mars is gonna get it before the sun finally dies. Okay, so basically, long story short, with all of these diagrams, is here's the storyboard. The sun used to be smaller and less luminous when it was born than it is today. Because of the process I described in the previous slide about the helium building up and the fusion becoming less efficient, the sun's core has to heat up, and that is slowly with time increase the luminosity of the sun and increase the size of the sun. And so today at stage 2, the sun is bigger than it was when it was born, and it's more luminous than it was. And you can see on the diagram where stage 2 is this very, very, this little step where the sun is rising upward on the H diagram. It's moving straight upward, if you will, from its current location. Now, between stage 2 and stage 3 is the stage where the Earth is going to have its runaway greenhouse effect. Okay, so at around 7.5 or 6.5 billion years from now, when the sun is about 6.5 billion years old, or about somewhere around 1.5 billion years from now or so, the Earth could enter a runaway greenhouse effect. And so that's shown, if you go to the diagrams on the right, by the little green shaded square that I inserted here, where it says Earth dies. Okay, so Earth dies around while the sun is evolving through this period from about 6 billion years to about maybe 8.5 billion years into its age. And as you can see, it's still quite small relative to the Earth's orbit in the lower diagram where it's in the red line. And you can see that its luminosity really hasn't increased all that much before the Earth is going to feel those effects. And then what happens after the Earth has had its runaway greenhouse effect is that the sun goes to stage 3 and becomes the subgiant, and it begins to expand drastically, and its luminosity tends to go up drastically. And so you see it move on the HR diagram from stage 3 to stage 4. And if you look at the diagrams on the right, you can see that's when the luminosity increases dramatically over a short period of only 300 million years. And the radius increases from about twice its present size to, at stage 3, to about the size of the radius of the Earth. And so that is the time when Earth will be evaporated and engulfed in the sun. Then I'm not going to bother you with all the other details, but the sun does shrink down again and its luminosity decreases at stage 5. And actually what happens is it starts fusing helium instead of hydrogen, so it sort of has a little heart bypass and starts its sequence over again in the core. But then eventually the helium builds up a sludge and it has to expand again. So the story starts over, and from 5 to 6, the star expands some more, but this time it really expands and becomes about twice the size of the Earth's orbit. There goes Mars, evaporated. Okay, and this is stage 6, so you can see stage 6 on their 2 diagrams to the right as well, and you can see how on the HR diagram to the left it goes from 5 to 6. And then eventually it hits this period where it hiccups that I was telling you about, and so that's this last phase from stage 6 to stage 7. And if you look at the diagrams on the right, the luminosity, the blue curve in the upper right, is going up and down, up and down, up and down, up and down about every 100,000 years. And the size of the star is going up and down, up and down. You can see in the red curve between 6 and 7 every 100,000 years or so. And so this is what causes the outer gas to eject. If you go back to the HR diagram, you can see the little picture there of the gas being ejected from the star. And effectively what happens after that is the only thing left over is the inner core, and it becomes something called a white dwarf. And you can see on the HR diagram that blue dotted line going around to the bottom of the diagram where it says white dwarf. Okay, so that's the story of our sun, and effectively I just wanted you to understand that walk-away information here. After you've listened to a great deal of discussion, walk-away information is the sun used to be smaller and it used to be less luminous. As it ages, it is slowly getting more luminous and it is slowly getting bigger. Somewhere around its age of 6.5 to 8 billion years, the Earth will have had and suffered a runaway greenhouse effect. And this is before the sun really bloats to be very, very large, meaning before it bloats to being the size of the Earth's orbit, which you should say happens somewhere around the age of 12 billion years. Okay, so we're at 4.5 billion years now, and somewhere around 12 billion years or 7.5 billion years from now, or 7 billion years from now, it is going to become very, very large indeed and engulf the Earth. Hi, before I move on with this slide, I just want to say that was a very long slide, that last slide, and a lot of details. For example, I named all of the different phases of the sun as it evolved. At this stage, I'm not asking you to memorize those things. I want you to know the story. I want you to know the walkaways that I said at the very end of the slide. So at the very least, play that part again if you want to know what is important, the walkaway information. Okay, which I won't repeat here, but you can listen to it again if you reverse the slide at some point or back the movie up. Okay, so this is our pretty close to the final slide. This is basically a discussion of how the habitable zone evolves in response to the evolution of the sun. Okay, so I guess I will repeat the walkaway information. The sun is expanding in size with its age, and its luminosity is increasing with age, which means the light energy and intensity is going up as the sun gets old. Okay, and so we talked about when the Earth was going to go into its greenhouse effect along that process between stages 2 and 3. But let's talk about this now in terms of the habitable zone itself. We're going to talk about how the habitable zone evolves. And I mentioned at the very beginning of the talk, and now we're come full circle to it, that as the sun ages and gets more luminous, the habitable zone will be further and further from the sun. It will move away from the sun. The other thing that happens, in addition to it moving further away, is that it gets thicker, it gets broader. In other words, the shell over which a planet could be in between in radius from the sun or distance from the sun gets thicker. There's more leeway there. So what I'm going to do is talk to you about the difference between the habitable zone and what's called the continuously habitable zone. Okay. Now, there are different definitions of the continuously habitable zone. I just want you to use the one that's in the notes. And so if the book has a different definition of it, that's okay. I want you to sort of think of it in the terms that I like to think about it. And so I'm going to give you my definition. Now, let's look at the diagram on the right, which is telling our story. On the y-axis there, we have distance from the sun, 0 at the bottom, and then 1 Earth orbit radius, and then 2, and then 3. So the distance is in Earth orbits again, or astronomical units. And you can see Venus's orbit at around 0.7 of Earth's orbit, and you can see Mars's orbit marked at about 1.5 times the Earth's orbit. Okay, and so a horizontal line across the diagram represents an object that's at that distance from the sun. So for example, you can see I put a red dashed line at 1 where the Earth's orbit is. So as we move along in time, which is what the x-axis is, in billions of years, as we move in time, the Earth would basically be on that line, and you could plot it on that line at different times. So when the solar system formed, the Earth would be at that point on that red line, but it would be above the time equals 0. And today, the present day is marked by the vertical black dashed line, and you can see that it intersects the time axis at 4.5, 4.6 billion years. And so that's the present day. So anything to the left of that line represents the past, and anything to the right of the line represents the future. Okay, so let's look at time equals 0, and we have, as we discussed before, a conservative estimate of the habitable zone and an optimistic estimate. It depends on whether you have the wet greenhouse effect or not. So let's look at the conservative estimate, the dark green. At time equals 0, you can see that the Earth was firmly located between the inner region and the outer region of the habitable zone. It's bracketed in the middle there. And as we move along in time, we remember that the sun is getting more luminous. As it gets more luminous, it means it's emitting more intensity in the light. And so this causes the habitable zone to move outward from the sun. Now the Earth is not moving away from the sun with time, so it follows that dashed red line as we move along in time. But the habitable zone, as we move along in time, is, you can see that green band is getting further from the sun. Its distance from the sun is increasing. And so if we move to the present time, 4.5 billion years from now, or sorry, to 4.5 billion years from when the solar system formed, we can see where the conservative estimate intersects that vertical dashed black line. And in fact, you see that it has the Earth at the red dashed line is just inside the inner region of or boundary of the habitable zone. We're talking about the conservative dark green one now. And so it's getting perilously close to the inner region of the habitable zone if we use that conservative estimate. Now, let's march forward in time beyond the present to the right of the diagram. The Earth is moving along that red dashed line. The habitable zone is moving outward, and we see that somewhere around 1 billion years from now, somewhere around 5.5 billion years or a little bit after that, the habitable zone is moved outside the Earth's orbit, and the Earth is now on the inner region of the habitable zone, if we're talking about the conservative estimate, okay? So that would mean that that's a point in time when we should see the runaway greenhouse effect have its onset. Okay. But now let's tell the story again, but from the optimistic greenhouse effect estimate, and that would be the lighter green band. And so you can see it's much wider. It almost goes all the way out to Earth's orbit there in the case of this particular diagram. And it includes even Venus's orbit. So it would have Venus and Earth both in the habitable zone. So you can see at time equals 0 that Venus and Earth were both in the habitable zone if the optimistic estimate prevailed. As time moves on, we now go to the present time, and you can see that Venus would be at the very, very inner lip or boundary of the optimistic habitable zone, and the Earth, of course, still well within it. And as we move into the future, Venus would move outside of the habitable zone. So clearly, the optimistic estimate is a little too optimistic because Venus definitely went runaway greenhouse effect well before the present day. And so this optimistic greenhouse effect and the broader estimate for the habitable zone is probably too optimistic. But if we follow the Earth into the future using the optimistic estimate, we can see that the Earth doesn't, I should put it this way, the habitable zone doesn't move out past the Earth's orbit until about 8 billion years from now. Okay, so that's where I've marked optimistic, about 3.5 billion years plus from now is when the greenhouse effect would take a place and become, I should say, a runaway greenhouse effect would take a place. So bottom line, our models predict that the greenhouse effect will become runaway somewhere between 1 billion and 3.5 billion years from now. Okay? And that's sort of marked here with this red-pink square that I put over the diagram. Now, like I said, we'll watch the movie and you'll learn that, in fact, it's very likely that photosynthesis is going to shut down only in about 600 million years from now, which isn't even 1 billion years from now. It's about half. So when the Earth is and the solar system is about 5 billion years old, 5.1 billion years old or so, is when the photosynthesis should shut down. But nonetheless, the runaway greenhouse effect is expected to start somewhere about 1 billion years from now to 3.5 billion years from now, even though the sun is still going to, live to be 12 billion years old before it's gone. The Earth will have become uninhabitable using this criteria of the habitable zone and surface water stable on its surface. Now I'm going to go back to this continuously habitable zone concept. Okay. So the continuously habitable zone is marked on the diagram on the right using the white dashed lines. Okay. And so what we see with those two white dashed lines, which bracket the red dashed line around the Earth's orbit, the upper dashed line, as you will see, intersects the outer region of the habitable zone when the sun was formed, when the solar system was formed at t equals 0 along the y-axis. And the lower dashed line, you'll see, intersects the inside of the conservative estimate at the present day. So if you look at the present day dashed line, and you look at where the inner region of the habitable zone is, you see that that white dashed line intersects there. That band between those two lines, you'll notice, are always inside the conservative estimate of the habitable zone. Okay, and so any planet that found itself in that range of distances from the sun, and the Earth happens to be in that range of distance from the sun, has been in the continuously habitable zone. That is a region, a range of distances from the star that have been in the habitable zone from the day the sun was formed and the solar system formed to the present time. And that's what those two white dashed horizontal lines are showing you. That is the range. And you can see the Earth is just toward the inner side of the range of the continuously habitable zone. So that's kind of good for us, good for Earth. But we're going to also talk about some data that show that this may also be a little bit optimistic, that in fact it's possible the Earth really wasn't in the continuously habitable zone. I guess the bottom line is, when you watch the movie, you'll see some information that is somewhat contradictory to some of the things that I've said here. And the point is, and this is a very important point about learning science, the point is not that, oh, these are facts, and I need to memorize these facts, and that's the way it is, and that we understand it to be that way. No, this is very tricky business. This is based upon complex calculations of physics, of chemistry, of evolution, of nuclear physics, of radiative transfer, of outgassing and plate tectonics, everything that goes into making climatic evolution of a planet like Earth, plus the evolution of the star, plus the interaction of the light from the star with the atmosphere, which changes composition with time. Need I continue? The list goes on and on and on. And so basically, somebody will tell you how something is based upon a model. And somebody's model might say, well, the habitable zone ranges from 0.85 to 1.4, and somebody else might say it ranges from 0.95 to 1.25. Okay, it depends upon the model. But the point is, we're getting better at it all the time, and the point is that we have a discussion here which really provides us some kind of future prediction about when the Earth is going to be runaway. Now, you're going to watch a movie called The End of the Habitable Zone, and it's going to talk about something called the faint young sun paradox. So I'm going to talk about that in the next slide. Alrighty, well, thank you for bearing with me. You've had 3 very long slides now, a lot of information in those slides. I know I must be getting very dry and boring to listen to, but I think that those 3 particular slides are the meats and potatoes of understanding what's going to happen with the Earth and its future, and what's going to happen with the solar system and the sun. And it's the real astronomy, the beginning of the real astronomy of this course. So I was talking about the fact that different models give different answers, but of course we're all barking up the same tree, learning things. So you're going to watch this video, The End of the Habitable Zone. It's a very good movie, worth watching multiple times as well if you're interested. I've seen it multiple times and still catch new things. One of the things that is going to be discussed is the shutdown of photosynthesis in 600 million years, and I just wanted to summarize the argument on that in these bullets. The first is that you're going to see that the Earth is heating up from the brightening of the sun, and you know all about that now. And so CO2 is going to be lost from the atmosphere, and the question now is, well, wait a minute, why? And that's going to be because silicate rocks that are being exposed by the evaporating oceans will absorb the CO2. He shows a chemical reaction that you don't have to know, but he describes it in a little more detail. And this process speeds up with increasing temperature. So it's a runaway effect, and this is going to remove most of the CO2 from the atmosphere, assuming that humans have stopped adding to it at that point. It will shut photosynthesis down when the concentration of CO2 reaches about 30 parts per billion. And for reference, today's carbon dioxide is on the order of 400 parts per billion. So we're talking about removing the vast majority of the carbon dioxide. And this helps lead to the conservative estimate of in the models for the habitable zone. The second thing in this movie that he'll talk about is the faint young sun paradox. And so the faint young sun paradox is based upon the idea that the sun was less bright in the future. And so according to the models that our host is using on the movie, this would very, very pessimistically, or I should say very, very conservatively, put the Earth just on the outside of the habitable zone. And that would mean that Earth should have been a snowball when it formed. We know that wasn't true. We have all kinds of evidence. And for example, life formed in liquid water about 3.5 billion years ago. And you may remember that zircon was found in Australia, which has been highly hydrated all the way back to 3.8 billion years ago. So water was, the slime ball Earth, if you will, happened very, very rapidly after the formation of the Earth and the end of the bombardment period. So how could this be true? And that's why it's a paradox. And so some of the solutions that are invoked is you have to evolve the Earth's atmosphere. You have to say, well, it would be outside the habitable zone when the sun and Earth formed if it had present day atmosphere. So that's the key to that statement. If the Earth's atmosphere didn't change, then in fact if it had today's atmosphere, it would be outside the habitable zone when the sun was not as bright in the past. So the idea is that you allow the Earth's atmosphere to be different, that it was more like the outgassing of the volcanoes that we talked about in the previous module about how the atmosphere was created and what its chemical composition was before the rise of oxygen. And if you use that atmosphere, you can actually get the habitable zone to be a little bit larger and, in fact, become consistent with the previous slides where I was discussing this model, that model. But for the Earth to have been in the continuously habitable zone, you basically have to allow the Earth's atmosphere to have evolved while you're making the calculation of the habitable zone as a function of time from when the Earth-Sun system formed to the present. And so that's what was shown on the previous slide. So again, the sun was less bright, and if Earth had today's atmosphere, that means that it would have been just outside the habitable zone and therefore be an ice ball. But it wasn't. It had water on it all the time, so it has definitely been in a continuous habitable zone. And one of the best solutions is to allow the Earth's atmosphere to have been different in the past and evolved. And so that is the faint young sun paradox, which is not fully resolved at this point in time. But I wanted to definitely share that with you. And to end our tour through the evolution of the Sun-Earth system and the definition of the habitable zone and the definition of the continuous habitable zone, including the faint young sun paradox, I end with pictures of planetary nebulae, or the nebula that result from that last death throw of sun-like stars, where they're doing their hiccup phase. You saw they rapidly expand and contract and rapidly go up in luminosity and down in luminosity, and they kick out their outer shells. Now, all of these are on the size of several solar systems in size. They're very large. And these are various stars that have gone through this process. I think one of the most iconic and ones is the Ring Nebula. And if you go to the top left and go one to the right, so the second from the left at the top, this is the Ring Nebula. And you can see that this is definitely a cloud of gas, spherically shaped, that is expanding out into space. And all of the atoms that were part of all of the planets, part of the star, part of any life forms that happen to be on any of those planets, whatever, they've all been evaporated into gas and they're expanding back out into space. And that, ladies and gentlemen, is our future. We will eventually, some astronomers will look up from some other star in the galaxy and they will see an object like this where our solar system used to be. Now, mind you, that will be in another, 7.5 to 8 billion years from now, but nonetheless, it's going to happen. The question is, will it be descendants of humans that are those astronomers? That would be very interesting. Of course, they would look nothing like we do today and wouldn't even remember the planet Earth. But nonetheless, I wanted to show you this little gallery from the Hubble Space Telescope, and I hope you will look at them. They're colorful, they're beautiful, they're expanding in velocity, and this is the remnants of our future. This is archaeology, if you will, of our future. Okay, again, don't forget to take the attendance quiz. I did the magic word at some point in time. You should have caught that. And then don't forget to take the lecture quiz at the end of that. And I hope you'll enjoy the 2 movies that I decided to show to go along with this module. I kept it down to just about 2 because there were 3 slides that were quite long, and I would recommend that you get the basic material out of those slides as you're watching the lecture. And yeah, so we'll see you next time. And don't forget, I have office hours Tuesday and Thursday at noon. I sit on Zoom, and so far I've had no company, but maybe I will before the exam. And of course, you'll be hearing this after that. Anyway, you all take care, and thanks for listening.